Okay, so this question is from 12. Winter B, question number 3. And in this question, wow, look really, really frightening. We have a capacitor, and this capacitor is connected to a solenoid. So they're going to talk to each other, right? The capacitor and the solenoid, okay? And you don't have any resistor here. This means that energy would not dissipate from circuits. It's locked there forever, okay? In the real life, of course, it's not the case. But if the resistance is really small, yeah, it's a good approximation depending on how long you're going to watch this phenomena. You're going to watch it forever, some energy going to run out, but you're going to watch it for 3 hours, 5 hours. Okay, maybe it's a good approximation. Okay, so, and here we have another solenoid. Okay, this is C, this is L2, this is L1. Here you have current which called I1, current that called I2, current that we're going to call just I. Okay, and what they ask us, okay, look, this thing, what energy going to do? They're going to be in the capacitor, or it's going to be on the solenoids, right? That's what's going to happen. A kind of a shift of energy, right? From electric to magnetic, electric to magnetic. And they ask you in the question, what is the frequency of the current? Let's do it in this manner. Okay, what's the frequency of the current? Okay? So in what way the current gonna get crazy in the circuit? Because the energy gonna move in some way. The way to move is current, right? So how are we gonna solve it? So every time you actually need to talk about the combination between them, we're gonna use the same law, which called Faraday law, okay? But before we're gonna do that, I don't need to solve that. I can solve an easier circuit. Why? Because these two solenoids are actually connected in parallel. So I can say, I don't care about each one of you. They ask me about the general current of the circuit. So I actually can unite them to one. Okay, so how it's going to look like? It's going to be just one C, right? And here it's going to be a magnificent L, right? And this L is equal to what? I want to remind you that L, the solenoid, is just a resistor. It's just like wrapping in some crazy geometry to produce magnetic field according to the right-hand rule. But it's just like a resistor. So when you sum up what is the total induction, it's the same as a resistors. Okay, that's what I want to say. So this thing is equal to what? To 1 over L1 plus 1 over L2 to the power of minus 1. Clear? That's it, I know it. I know what is this carry L. So the L is actually equal to what? To L1, L2, L1 plus L2, and that's it. I finished the question, right? And now it's a really easy circuit. Okay, great. So now let's deal with this circuit. So the way to deal with the circuit is actually using Faraday law. What Faraday law said? So Faraday law said that the loop integral on the current equal to the change minus the change of the flux, dt. You see it? And we're going to do another question regarding that topic, okay? Because it's really important. I really love Faraday equation because Faraday equation is the equation that actually connect electromagnetism, and magnetism. Because this side is actually talking in the terms of electro, right? Electric field. And this term talking in magnetic. So this is actually the conversation. In this equation it's happened. Okay? Good. What is the formula of phi b? What is it? Exactly, it's corrected. But in our case, we have an inductor. Inductor actually give us some breakthrough. And we can immediately talk about the current, okay? What we're actually saying is that all the magnetic phenomena actually taking place inside the inductor. Forget about the circuits, it's negligible. That's the concept, okay? So I can change this term into minus dIL divided by dt, right? L, I'm gonna say it's a constant, and let's leave me with L, the total one, right? I dot. Good? We got it. Now we need to see where there's accumulation of electric field in our question. A capacitor, that's what capacitor do. It actually holds electric charges that produce electric field. So here we have some electric field. So pluses actually accumulates here, right? And produce electric field, right? That's a concept. Okay? And I didn't tell you this, but they say in the question that the time equals 0, on the capacitor there was already charge. The charge was this number. Okay? It's a given thing. Okay, so this is the charge. Good. And right now, I'm gonna do this integral. What this integral require to do? Drawing a loop. Drawing sorry, I forgot here to put this. What this mean? That the loop must be closed. You start here, great. Go whatever you like, but don't forget to come back to the same place. That's the idea. Okay, so I'm gonna choose this direction, right? I'm gonna choose this direction, right? Good. So actually E multiplied by DL is a voltage. We have a voltage drop only here, which is VC, the voltage of the capacitor, right? What is voltage of a capacitor equal to? We can connect it to the charge, Q. Why we actually want to connect it to the charge? Because I talking in the language of the charges, right? You see it? So I want to make them talk to each other, okay? Great. So this one is actually equal to Q divided by C of my capacitor, right? And this is the charge on the capacitor. You see it? This is equal to minus L, and I is actually the change of charges, actually the second change, because I equal to dq dt, right? So this is second derivative. Okay? Good. Now I want to reorganize this equation. Yeah?
Why does the E dot dl equals the voltage?
Okay. I like to think about the electric field unit as, let's go here. Electric field is actually voltage divided by distance. This is the concept. If I'm going to take two wires, okay, with let's say thousands volts, and I'm going to put on somebody, this is the electric field. The electric field is the distance between them. How I do lighting, okay, there's some electric field that actually is so strong that conducts electricity through air. Insane. So when I'm going to have two wires and I'm going to put them really, really close, I'm going to see this sparking. Okay? When you plug something into the wall, right, you see sometimes that when you just plug it, you see some light, right? This is the concept. You decrease it. So I want to remember that electric field is actually volt, which represent the energy, kind of, right? It's energy divided by charge, per some distance. So this integral actually tell you to sum up the voltages in the circuit in a more precise way. Okay, some people write here sum of the voltage, Kirchhoff law, the second law of Kirchhoff. I don't like it, honestly, because it's not clear what is the direction. Here it's clear. Okay, this is a basic. This is the Maxwell equation. It's really like solid, right? Good. And and Kirchhoff law tell you that this is equal to 0, which is wrong. It's equal to the flux of the magnetic field. Usually Kirchhoff questions do not deal with magnetism. Okay? So, but this is hold whatever you're gonna do. Okay? In any situation, this is hold. Okay? Good. So let me write it differently, and then I want you to be really careful, and I want you to notice something really special. Okay? Let's do it here. Great. So I'm going to write it that way. Q dot, be careful, look at that. Look what we have here. Plus 1 over CL Q equals 0. What is this? This familiar? What is this looking like? I'm going to give you a hint. You want a hint? I think I write it here. Really important in science and engineering to see this and said, fuck that, I know what is it. That's what I want you to feel. If I had a spring, right? Here's the spring, and it's moving in that direction, right? It's doing this wiggling motion. So if you're going to do Newton equation, we're going to find out that it's moving like that. Right? And if we had some pendulum that's actually moving that way, which transfer potential to kinetic energy, that's what, this energy to this energy, this energy to this energy, right? Spring to be relaxed, spring to kinetic, spring to kinetic, spring to kinetic. This one is actually theta plus G L theta equals 0. What is this called? Not the wave equation. No, you're not in interdirection. Okay, it's a really hard equation, the wave equation. This is an easier one. This is harmonic oscillation. Simple harmonic oscillation. Okay? Simple because the solution is a science or cosines. Okay? What I did here, science. Let's use that. Yes, I did sinus. This is, what is the solution? What we are looking for? Let's make it clear. When you have this thing, when you see this thing, immediately I want you to have the solution. Immediately, I don't care which class you are, okay? Immediately I want you to say, okay, I can find the solution of that. This is Q. It's equal to some constant, which have the same units. Let's call it A, okay? A, let's call it Q0. Because we know in some time, the capacitor have this quantity, okay? Sinus time, okay? Simple means sinus, okay? The most easy thing that we have, and also have some periodic, right? Simple harmonic motion, okay? So this, and I want to talk about these two terms. Different color. I don't have here colors. Okay, I have this. This is black. It's going to be good. Okay, this is, I called it omega heart. Omega heart mean the frequency, how much time play a role, okay? If this is thousands, okay, 10,000s, and this is 1 second, this is actually 10,000s, okay? So this tell how time actually play a role in the game, right? And this actually equal to the square of that. You see here, what is the fight between the spring and the mass, right? What is the fight here between gravity and the length of the pendulum, right? And here the fight is between capacitor and inductor. I want the energy. No, I want the energy. That's what they are doing, okay? Electric, magnetic, electric, magnetic. So this called the frequency, okay? That's what I want you to know. Okay, so this is equal to what? In this case, omega equal to the square of k divided by m. In this case, omega heart equal to square g divided by L. And in our case, it's equal to, right? That's what we have. So this is the frequency of this term. I want to remind you that in our equation, we actually have a really fucked up inductor, right? We have two inductors that we messed them up together, and we have this one, okay? So in actually to solve the question, we need to put the right one. I want also to say that here, why put here a sinus? Somebody know why I put a sinus? No, there's no way for you to know, because I just put it there for no reason. Because I can put here whatever I want if I'm gonna put a correction factor. Okay, that's the concept. What this is correction factor? What actually sinus said about the period? Okay, sinus said that I'm nothing. Okay, for example, we look at the case where we don't have charge. I'm zero charge, and then I'm gaining charge. Okay, that's what it said. If I had here a cosinus, it means that I already have all the charge that I want, and now I'm going to lose it, right? So phi actually correct us if this sinus is wrong. Okay? In our case, it's wrong. We start with a t equals 0. we actually had everything we need. So if you're going to put the initial condition, the time initial condition, what's happened in the beginning, if you're going to put Q at time 0, we know it's equal to Q0, and that's going to give us phi equal to pi over 2. Okay? And you can write here pi over 2, and you can also say, okay, let's do geometry and change it to cosines and forget about phi. Okay? So, but I want you also to notice that in life, nobody said that we're going to start with everything or with nothing. It could be something in between. So phi can sometimes be pi divided by 4. Okay? I don't know where I am taking the video, where's the video started, right? Where's the time the stopper start to run? Okay? So this concept is this. Here you just plug, I have it here. Okay, you just put the L total that we calculated here, square root, and we have the tempo. Something that people can do in the exams and really love it. We found the charge. What charging time tell us? If I know how charge is changing in time, I can know the current. So sometimes people can ask, what is the current, right? So you just need to derivative this concept, but I want you to notice that it's going to move in the same frequency, right? Because sines and his derivatives actually moving in the same manner, right? If I'm going to derivative sines, I'm going to have cosines, which are going to have the same thing here, right? And then some people can ask about energy, okay? What is the energy? What's changing the energy? Or other stuff to use the current for something else. So this is the higher ways to take this formula, this question to be a little bit harder, okay? What is the maximum charge? What is the maximum current? What is the maximum energy? What is the maximum power? Okay? It's clear? Where people can take it? Okay, good. So this was this question. And now, okay, let's do that. That's also a good question. Okay. Can you stop the video and start again?